Hi, my name is Cameron Hurd, and this is my report on our fourth lab for Physics 2211, which deals with oscillations. For this lab, I observed the oscillations of a weight attached to a spring when released from rest, and observed how accurately a computational model can predict the motion and energy changes associated with that motion. In this presentation, I will explain the fundamental principles involved, detail my observations and computational model, compare the model to my observations, and connect both back to the physics principles. So to start off, the fundamental principles associated with this lab are Newton's second law, or alternatively the momentum principle, as well as the energy principle. Newton's second law states that the net force acting on an object is equal to the object's mass as well as the acceleration. And alternatively, the net force is also equal to the change in momentum over time. The energy principle states that the change in the total system energy, the total energy of the system is equal to the work acting on the system. Now I'll go into my observations, which I record and analyze in Tracker. Here I've set my coordinate axes to be right, the origin to be right at the attachment point of the spring, and I've calibrated my data based on this calibration stick of 0.7 meters, 0.7 meters, based on the distance between the attachment point and the center of mass of the weight when it is sitting motionless. Here you can see how the weight oscillates back and forth when it is released from rest. Now I'll go move on to my code. Here, for this model, we assume the forces acting on the weight are the weight force and the spring force, and that the mass of the spring is negligible. Here I've set up my initial conditions, such as the mass of the weight as well as its initial position and velocity. I start at time equals 0. Here I have the gravitational force constant as well as the spring constant, and then the initial and final lengths of the spring. Here we assume that the system in this case is the spring, mass, and the earth, and so the system energies involved would be the kinetic energy, the gravitational potential energy, as well as the spring potential energy, which all these add up to equal the total energy. In the real life setting, we would assume that the total energy, the total change in energy in this case would be 0, because the only interaction with the system, being the attachment point, does not go under any displacement, which means no work is being done, and therefore no change in energy. I then loop through to go find the gravitational force and spring, and eventually get the net force, which I then use to update the velocity, position, and then the system energies to go find the change in energy over time. And if I run this program here, we can go see the model as well as the experiment, the comparison between them, the model being in blue and the experiment being red. Here we see that the total change in energy is 0, indicating that the system energies cancel each other out, and that in fact there is no work being done on the system. We can see how each of the individual system energies oscillate back and forth and eventually sum to equal 0, which represents the delta E, the total change in energy of the system. Here we can see the position versus time graphs for both the X and Y data for the modeling experiment. While we can see the model roughly predicts the observed motion, there are still discrepancies. This may be due to dissipative forces acting on our system, which would eventually stop the motion of the mass and decrease the magnitude of the system's individual energies over time. It could also be due to, in part, because of small inaccuracies in the point mass data that I procured from Tracker, as well as slight errors in the calibration stick or potentially the camera's angle. Looking at the graphs, we also see that the frequency of oscillations is different between the X and Y data. They are not aligned with each other. After taking the average of the periods between each peak, for each axis, I found the average period to be 1.646 seconds for the X data and 1.519 seconds for y data. My line of reasoning as to why this is the case is because I believe the mass is closer to static equilibrium along the y-axis than it is along the x-axis. We see this in real life with basketballs, how when you bounce a basketball, it will slowly start to decrease in height over time as it dribbles, and that the period between it bouncing starts to decrease and decrease as it over time. And we can see that as it bounces, if it's being launched from an angle, a lot of times it will come to rest along the vertical axis before it does so along the horizontal axis. So it'll end up rolling on the ground before it stops completely. Thank you.